Welcome to Engineering Project Management Insights. Today, we explore quality management as detailed in Chapter 12 of the Handbook. I'm Dr. Valerie Denny, and in this episode, we will examine how this competency enables practitioners to build excellence into every project phase and deliver reliable products that perform as promised in the real-world conditions. Let's get started. Quality management competency is an element of the strategy and systems pillar of this handbook. As we explore Chapter 12, we address the reality that in engineering, success is measured by more than just finishing on time and under budget. Success also depends on meeting tight tolerances, safety margins, and strict standards that protect both people and the environment. Our guiding question for the slide and the central theme of the entire competency is, are quality assurance processes properly implemented? When you review the handbook in detail, you will find stage-specific questions. For example, during selection, we ask, what are the requirements to maintain quality assurance? In the transfer stage, we ask, is the delivered product complying with the customer needs? Modern quality management requires shifting our mindset from simply testing quality in at the end of production to building quality in through effective process control. This means planning the work, tracking progress, and addressing issues in real time to ensure every deliverable follows standards and satisfies stakeholders. In this chapter, we explore 4 quantitative and 17 qualitative techniques. Because the full list is extensive, we've selected 5 essential tools every engineering project manager should master to ensure effective process control turns quality requirements into reliable engineering outcomes. First, the quality management plan provides a roadmap defining exactly how we will measure success for this specific project. To maintain stability during execution, we rely on control charts to monitor our processes in real time, ensuring we only intervene when data shows unusual variation. When resources are limited, Pareto charts guide our focus by highlighting the vital few problems causing the majority of the defects. We validate our process through disciplined design reviews, using structured technical checkpoints to catch errors early when they are significantly cheaper to fix. Finally, when issues do emerge, we use root cause analysis. Here, we show the 5 whys to move beyond surface level symptoms and fix the fundamental problem. Together, these tools empower the engineering project manager to build quality in throughout the project lifecycle. Let's explore the fundamental concepts of quality management, starting with our core engineering insight. Modern quality management relies on effective process control, not just inspection. Our first graphic, the quality domain, clarifies the 2-part system every program manager should understand: quality assurance and quality control. Quality assurance is our proactive, process-focused prevention where we use planning and auditing to build quality in from the start. Quality control is a reactive, product-focused detection where we use technical verification and testing against specifications to test quality in before delivery. The second graphic illustrates the quality shift required. Rather than relying on reactive models of finding defects through final inspection, effective quality management emphasizes a proactive approach that builds quality into the process. Through disciplined process control, design reviews, and early verification, we prevent defects instead of simply detecting them after they occur. This shift is also driven by a powerful economic reality, the 1-10-100 rule of quality. Every dollar invested in prevention can avoid approximately $10 in rework during development and as much as $100 or even more in post-delivery costs, such as warranty claims, recalls, schedule delays, and reputational damage. The lesson is straightforward. Preventing defects is not only better engineering, it is also better business. Let's look at more of the fundamental concepts on the next slide. Continuing with our fundamental concepts, we turn our attention to the practices that sustain engineering quality throughout the project lifecycle. On the left is the Plan, Do, Study, Act, or PDSA cycle, the engine of continuous improvement. Rather than treating quality as a one-time activity, this iterative process helps engineering teams plan improvements, pilot changes, analyze performance using data, and standardize successful practices before beginning the next cycle. On the right, we see how technical excellence is achieved in practice. Disciplined design reviews, for example, a system requirements review, preliminary design review, and a critical design review, provide structured checkpoints that identify issues early when they are far less expensive to correct than after production. These reviews are effective only when supported by a strong quality culture. Transparency encourages open reporting of risks and defects. Accountability makes quality everyone's responsibility. The stop work authority empowers every team member to halt work whenever technical integrity or safety is at risk. Together, continuous improvement, disciplined design reviews, and a strong quality culture form the foundation of engineering quality management. The handbook identifies several practical applications of artificial intelligence that are already transforming engineering quality management. First is an automated compliance. Fraunhofer has reported that generative AI can produce ISO-compliant test cases for 500 safety requirements, reducing a task that previously required 20 person days to just 8 days. AI also accelerates quality processes. NASA documented that AI can draft complex process documentation and audit checklists in minutes, effectively cutting in time spent on administrative quality preparation by about half. Beyond documentation, AI enables predictive design. By analyzing CAD models, simulations, and engineering data, AI can identify potential design weaknesses and tolerance issues before hardware is ever manufactured. We're also seeing the emergence of AI quality co-pilots. These systems continuously monitor and change control data, helping teams identify trends and reportedly predict potential quality defects with more than an 80% precision. The key takeaway is that AI augments engineering judgment. It does not replace it. Engineering project managers remain responsible for validating AI recommendations, protecting proprietary engineering data, and ensuring that every quality decision is supported by sound engineering principles. Today, engineering projects often span multiple countries, adding layers of complexity to our quality efforts. Our core insight here is that effective global quality management requires navigating layered regulatory landscapes and securing tiered supply chains. Engineering project managers should identify all relevant standards across jurisdictions and build their quality management plan around the strictest requirements. This proactive approach prevents costly late-stage redesigns when a product must enter a more regulated market. Second, we must look for hidden. The handbook identifies 8 connections to quality management. It starts with requirements management, which provides the testable specifications we must meet. These are tracked through project controls and balanced against the project's value via financial management. We also see a deep tie to risk and safety management, where we proactively design out potential failures. However, these technical links only work if we have the leadership to empower the team and clear communication required to share the results across the project. Finally, we must manage our resources effectively to provide the right tools for precision, all while grounding our decisions in ethical and professional responsibility. By connecting these competencies, the engineering project manager ensures that quality is never a standalone task, but a continuous thread throughout the project lifecycle. In this chapter, we examine real-world applications through 3 case studies that illustrate the challenges of maintaining technical excellence in high-stakes environments. Here, we focus on the Interstate 95 Philadelphia Rapid Rebuild, which underscores our engineering insight. Crisis speed must never bypass disciplined quality verification. When a fire collapsed a major overpass in 2023, the team reopened 6 lanes in just 12 days. This success demonstrates that even under extreme schedule pressure, technical leads must not waive requirements. Instead, they must rely on pre-approved emergency materials and staged acceptance to ensure speed does not introduce failure. By using foam glass aggregate for backfill and load-tested high-strength concrete within 4 hours of the placement, the team maintained workmanship while creating a public audit trail. This case proves that quality discipline is exactly what makes rapid, safe recovery possible. Along with the other case studies, this example reinforces that discipline is essential for delivering reliable products that perform as promised. On this slide, we address some implementation challenges that can derail even the best plans. Our engineering insight is straightforward. Disciplined process control defends against compounding costs of technical failure. The first challenge is the reactive track. It is tempting to rely on final inspection to catch problems, but effective quality management shifts the focus from inspecting defects out to building quality into the process from the very beginning. Another common challenge is currency and schedule pressure. Building hardware while the design or software is still evolving often creates an expansive cycle of rework and retrofits. We must overcome integration gaps. Disconnected engineering tools, incomplete digital models, and limited end-to-end testing can conceal defects until they become much more difficult and costly to correct. Engineering project managers must also manage supply chain risks. Quality problems can originate beyond the first-tier suppliers, making visibility, audits, and verification throughout the supply chain essential. Finally, we must resist eroding discipline. During schedule crisis or intense public pressure, the temptation is to waive requirements or shorten test windows that can be strong. Effective engineering project managers protect the quality gates that safeguard technical integrity, safeguard, and long-term project success. We conclude our exploration of quality management, Chapter 12, with 5 terms every engineering project manager should know. Our engineering insight here is that precise terminology is the foundation of effective quality communication. First, as we've discussed, we must distinguish between quality assurance, our proactive process-focused prevention, and quality control, a reactive product-focused detection. While QA builds in quality, QC ensures nothing defective reaches the customer. Next, we use the cost of quality framework to justify our technical discipline, balancing the relatively small cost of prevention against the catastrophic cost of failure. We sustain this excellence through the PDSA cycle, an iterative model of plan, do, study, act, to refine our processes based on real-world data. Finally, we master statistical process control, or SPC. This technical discipline moves us beyond guesswork by using data to monitor process stability. By distinguishing routine noise from unusual variation, we can implement the real-time corrective actions required for technical excellence. Thanks for watching. If you haven't already subscribed, I'd appreciate it if you would do that.